In the last class, we have seen that even for the simplest possible machine which uses a single slider mechanism, the exact representation of the unbalanced forces and moment is a complicated task. However, the situation is saved by the fact that it is possible to make some approximation without introducing too much of error, and the problem can be somewhat tractable. What we have done is that we have replaced the actual connecting rod by an equivalent connecting rod consisting of two particle masses at the two ends placed at the slider pin and at the crank pin. So, we have placed M A at this point A and M B at this point B along with the slider, and this becomes a massless rigid rod. In the process, what has happened that all the matter contained in this mechanism or machine is now divided into two parts. One part is a purely rotating object which can be easily balanced by providing a counterbalance opposite to the crank. And once that is done, what remains is only this matter or this mass or slider which is executing a reciprocating motion. So, then we have seen that if the acceleration of this be x 2 dot in this direction, then the inertia force obviously will be acting in this direction. It is obviously simple to look at and much simpler to handle, but even then we should not forget that the expression for x 2 dot itself is again the expression of x 2 dot itself again is an infinite series, and even for a smooth operation where the crank rotates at a constant angular velocity, the x 2 dot will be an infinite series containing all the higher harmonics. We have seen that the inertia force or unbalanced force is given by only its x component. So, we call it f x, y direction unbalanced force because of this rotating mass has been taken care of by this, and this is equal to it will have two parts. Or in a way we can say that force is acting in this direction, that means f x, that is the force acting on the whole system as an inertia force in this direction, if we call as f x, then f x is nothing but m reciprocating omega square r cosine omega t plus lambda m reciprocating by 4 2 omega square r cosine 2 omega t. And I think to indicate that it is not exact, but it is approximate, as we have removed the or ignored the high harmonic terms. This we have called the primary and this is called secondary. So, in most cases, as mentioned earlier, it will be enough for us to consider up to secondary, until and unless we go to such situations where much higher accuracy is required, like say aero engine and such cases where we must have far more accuracy than a normal auto engine or other machines like stamping machines, punching machines or compressors. Now, what I think we will do next is that try to represent, which will be useful at a later time, that try to represent the inertia force due to this reciprocating mass with the help of rotating counter or by the help of rotating vectors, as we have done for the harmonically varying functions of time in many cases. So, as you can see that this primary force so, if we consider that the reciprocating mass has been kept at the crank pin and this is the crank which is rotating with an angular velocity omega like the actual crank, and therefore, this angle will be omega t. If we consider the initial condition, that means at t is equal to 0, the crank was aligned with the center line of the engine or the system. So, then what will happen, that this rotating mass will produce an inertia force which is equal to and its component along the x direction if we call it primary will be equal to now, of course, we have to all the time keep in mind that it is only this component along x direction that is what is really existing. The cross component in the y direction is not existing. Now, this will be useful only when we solve problems with multiple cylinders or engines and try to arrive at results employing the same kind of techniques what we have used in rotary balancing. Now, if this is the primary component of the unbalanced force produced in the system, what about the secondary? Now, to represent the secondary one, we use another crank and we keep the mass which is lambda m reciprocating r by 4, not r, sorry, at an r distance. So, it will be m reciprocating by 4 into lambda at a distance r, and we call this as a secondary crank. This is the primary crank. These terminologies will be useful at a later time, and let us allow this secondary crank to rotate at a speed double the speed of the primary crank. That means, with a speed 2 omega. And if we use the condition that at time t is equal to 0, secondary crank was also aligned with the x direction, then the angle, this angle will be simply 2 omega t. Okay, fine. What is the force here? So, this is 2 omega t. The force which is produced by this rotating mass in this case is again a centrifugal force or unbalanced inertia force, and that magnitude is lambda m reciprocating 2 omega square r by 4, and its component along the x direction, which we may call as secondary force, unbalanced force, which will be equal to thus we can see both the secondary and the primary forces can be imagined to be the components along x direction of a hypothetical two masses placed at the tip of the primary crank, which is the actual crank, and a secondary crank which rotates at a speed double that of the primary crank and of same radius. Then these components along the x direction will be what we get in the real system or actual single cylinder engine with connecting rod replaced by a hypothetical connecting rod of 0 mass and particles at the two ends. Now, for balancing these forces, what we can feel now, that if this force is being produced by as a component of the force produced by this rotating mass, then what happens if we apply or put, if we put a counterweight to this. That means, now let us see this is our single slider machine. The rotary part has been already balanced by a counterweight, and I am now putting another counterweight, which is m reciprocating r. That means, the unbalance kept here, the product will be equal to this. Then what will happen? The unbalanced force produced by this is in this direction, which is m reciprocating omega square r cosine theta, and this will produce a force m reciprocating omega square r, and this component will be m reciprocating omega square r cosine theta. This angle is theta, and this component will be this. Now, what is happening that the actual original unbalance due to the reciprocating mass and the centrifugal unbalanced force produced by this balancing mass attached as a counterweight, what it is going to do in effect, that the resultant system will be now subjected to an unbalanced force which is in the y direction. So, this system now the unbalanced force is in the y direction. So, what we have done to balance the force in this x direction has been balanced, but a force in the y direction has been generated. So, this is not exact satisfactory situation, but sometimes this is useful where a force in this direction may be less desirable than a force in this direction. For example, suppose the mounting of this machine or the engine is something like this. And if we have the engine here, then a force in this direction may be less acceptable from the point of view of vibration of the support structure, whereas a force in the normal direction, in this direction, may be more, I think it may be preferable, because the support structure may have much higher rigidity in the direction normal to the ground. So, therefore, if we can generate a force in this direction, but completely remove the force in this direction, is sometimes an acceptable solution. The other solution which of course can be considered, which is that you do not completely nullify the x component of the primary unbalanced force, but only a fraction of it. So, in that case, now here this will be say some fraction, say let me take this, say chi m reciprocating r, where chi is less than 1. So, what will happen here? This force, what will be generated will be chi m reciprocating omega square r, and the unbalanced force in this direction is m reciprocating omega square r cosine theta or omega t cosine omega t. So, then what happens finally, the system will have a smaller force in this direction, and in this direction so the engine, if we represent by this outline, so the unbalanced force in the engine in the x direction is this much, which is obviously less than this, but we have also produced another unbalanced force in the y direction, which is also less than this in magnitude. So, sometimes this partial balancing is adopted. So, to reduce the level of the amplitude of the oscillating unbalanced forces. However, you can also stretch your imagination and think or consider a complete balancing of the unbalanced force. Now, complete balancing of unbalanced force if we have to do, then obviously two things you have to keep in mind, that you have to neutralize the force without generating a force as we have done in this case by adding a simple counterweight. And secondly, we have to also keep in mind that in this way we have only neutralized the primary force. To neutralize the secondary force, again what we have to do, we have to create physically another crank which will be the secondary crank and add another mass, but I think then the system becomes very complicated. However, in very special situations where it is absolutely essential to neutralize as much force as possible, we adopt such techniques. This technique is called often as Lanchester balancing technique. This is our single slider system. What we do? We first So, here we have attached a gear 1 of some radius. We have attached or connected an identical gear with this like this, which is again a composite one with a smaller gear attached to it directly. So, if it is gear 1, this is gear 2, this is gear 3, this is gear 4. So, here 1 and 2 are identical. Then 3, 2 and 3 are attached. Three and 4 are identical. Now, this angle is theta. What we do now? We attach two masses and these masses are m reciprocating r. These unbalanced quantities which are given are equal to m reciprocating into r. That means, the product of this mass and this eccentricity, the product of this mass and then this eccentricity, they are equal to m reciprocating r. They are also placed in such a manner, they make angle, that means, this line joining these respective centers with these masses with the horizontal line like this, they make theta angle, which is same as this. Now, let us consider the motion. Since this is rotating in this direction with an angular velocity omega, this gear 2 and along with that 3 will rotate in this direction same speed omega. And since 3 and 4 are identical, this will also rotate with a speed omega. So, now what happens that this will produce a centrifugal force m reciprocating omega square r. This will also produce and the resultant of these two forces will be what? Sorry. I am sorry that it should be half. Then the resultant will be m reciprocating omega square r cosine theta. The x component of this is in this direction cosine theta, half m reciprocating omega square r. Component of this along x direction is again half m reciprocating omega square r cosine theta combined, that is the force, and this is produced, this has produced at this instant a force which is so this force, unbalanced inertia force generated by the slider and the resultant of the unbalanced centrifugal force produced by these Lanchester balanced masses placed here, will neutralize the effects of each other. As you can see, the resultant of this and this will be in this direction, the y component of this and y component of this will be neutralized among themselves. So, this way, and you have to also keep in mind that they must be aligned, so that they do not produce a couple. So, in this gear systems and this unbalanced mass system can completely neutralize the primary. Now, if we are taking that much of initiative to neutralize the primary force, it will not be appropriate to leave the secondary unbalanced force without any compensation. So, in such cases what is done? In such cases what we can do? We can So, in such cases what we do? We put another pair of gears whose radius is half the radius of gear 1, 2. So, this it is say 5 and this is 6. So, 5 and 6 have radii half of that of 1. So, what will happen if this is rotating with an angular velocity omega in this direction? This is an idler gear. So, this will rotate in this direction, then this will again rotate in this direction and this will rotate in this direction, but the speed will be now 2 omega. So, these two gears will rotate at speeds double the speed of the crank, and what we can do? We can attach some masses here, which is lambda by 8 m reciprocating into r. Same thing here, lambda by 8 m reciprocating r will be this, and the angle is such that this is 2 omega t. Similarly, this will be 2 omega t, that at time t is equal to 0, they are all aligned. This was here, this was also here. Now, since it is rotating at 2 omega speed, this will rotate through an angle 2 omega t, this will rotate through an angle 2 omega t in the opposite direction, and what will be the force produced here? Of course, and this force is lambda by 8 m reciprocating r 2 omega square, same is this, and the resultant in this direction will be cosine component of this, cosine component of this, y components are neutralized among themselves. So, it will be lambda by 4 m reciprocating r 2 omega square cosine 2 omega t, and the secondary force in this direction was lambda m reciprocating omega square r cosine 2 theta. So, you can find that omega t equal to theta. So, this will again completely at every instant will neutralize the secondary. So, the primary is being neutralized by this set of balanced masses, and the secondary is being balanced at every instant by this set of balanced masses. So, this way we can find that a complete balancing of the reciprocating unbalanced forces of a single cylinder machine can be achieved up to the secondary. However, of course, as I mentioned that this active balancing technique developed by Lanchester first or proposed by him is a very elaborate arrangement, and it is done only in very special cases. In normal situation, we always try to go for simplest possible mechanical construction, that means in the form of a counterweight, where you can either convert the horizontal or x component of unbalanced force into a y component, or you partially balance it so that little bit of x component unbalance remains and little bit of y component is generated. Now, situation is much better, as we know, when a machine is designed keeping its smooth functioning in mind, in such a way that we do not use a single slider system. If we use multiple slider systems, then you can really appreciate the fact that it will be possible for the unbalanced forces generated by the reciprocating masses in the various components of that machine, that means each one composing one single slider system, they can neutralize among themselves. That means the whole system will be self balanced, and that is why you will find that in engines where you have more than one engines, or compressors where you have more than one cylinders, this technique is employed, where the unbalanced forces of the various cylinders or engine parts will be balancing among themselves, and this we will take up in our subsequent discussions.